After studying this module, you shall be able to know what is radioactivity and how does it pollute the environment, learn the various sources of radioactive pollution, gain knowledge about waste management.
Dear students, in this module, we will discuss about radioactive pollution. Radioactive elements come about naturally in the environment from the weathering of atomic minerals. Another significant source of production has been the cosmic rays, its interaction with matter that produce tritium and radiocarbon. The phenomena of radioactive emission has been recognized with the instability of nuclei of heavy elements. The three main types of emissions from radioactive substances are alpha radiations, beta radiations, and the gamma radiations. Out of these three, the effect of alpha radiations, which are also called alpha particles and are in fact helium nuclei, is the lowest, and that of gamma rays is the maximum, beta radiation having an intermediate impact. Alpha particles can be blocked by a mere sheet of paper, while protection from gamma particles needs thick lead plates. The accidental ingestion or injection of alpha particles can be lethal, since they come in direct contact with internal organs and blood. Radiation is harmful only when it comes in direct contact with the body. If the radiation is blocked, the presence of radioactivity is not destructive. Radioactivity is the spontaneous emission of energy from an unstable nuclei. This spontaneous emission, known as radioactive decay, continues till a stable non-radioactive configuration is achieved. Radioactivity is generally expressed in terms of, the first unit is Curie. Curie is the unit of decay of an isotope which is equivalent to 3.7 into 10 raised to the power 10 disintegrations per second, and by convention is equal to the decay of 1 gram of radium. Smaller units of Curie are also used for practical purposes, such as microcurie, which is 10 to the power minus 6 Curie, nanocurie, which is 10 to the power minus 9 Curie, and picocurie, which is 10 to the power minus 12 Curie. The second unit in which radioactivity is measured is in terms of rad. Rad refers to the dose of radiation absorbed, which equals to 100 ergs of energy absorbed by 1 gram of irradiated matter, that is 1 joule per kilogram. The third unit for measuring radioactivity is rem. It refers to Roentgen equivalent in man, that is a quality factor which is used in human health to measure the relative effectiveness of different radiations to create some biological effects.
Sources of radioactive pollution. The exposure to radiation occurs via sources categorized as natural and anthropogenic. Natural sources. Natural sources comprise of cosmic rays and radioactive compounds in the soil and their residues emitted into the air, water, and food. Our body cells also emit natural radiation in the form of K40. At higher altitudes, the thinning of atmosphere provides lesser protection against the cosmic rays. Anthropogenic sources. Nuclear power stations are responsible for production of radioactive waste. Nuclear waste produced from nuclear power plants may generate low to medium radiation. This result contamination to air, water, and soil. Radioactive wastes are harmful due to the fact they cannot be degraded chemically or biologically. In Europe, the nuclear power plants are the biggest sources of man made nuclear waste in the surrounding ocean. Radioactive traces from these plants have been found as far away as Greenland. Mining and refining of ores of radioactive elements such as uranium and thorium involve crushing and producing of radioactive ores to generate radioactive byproducts. This nuclear fuel cycle is used in many industrial, medical, and scientific processes. Nuclear explosion in 1986 at former Soviet nuclear power plant from Chernobyl and in 1979 at Three Mile Island nuclear power generating plant near Harrisburg, PA are two well-known nuclear accidents in the history. The effects are still seen today. Industrial uses. Due to modernization of radioisotopes has been increased in a variety of ways in order to improve productivity and to gain information that cannot be possible in any other way. Short-lived radioactive materials are required in flow tracing and mixing measurements. In environmental management, nuclear techniques are used rapidly. The continuous analysis of rapid response of nuclear techniques, many involving radioisotopes, mean the reliable flow and analytical data can be constantly available. This results in reduced costs with increased product quality.
Exposure pathways of the radiation are manifold. Contaminated water and food dusted with fine materials carried by the air can result in ingestion of alpha and beta particles, which are really dangerous when taken into the body through food, water, or air. Proximity to radioactive materials, not only loosely secured dumps but also roads or other structures built with mining wastes, can result in exposure to gamma particles and neutron radiation. Radioactive pollution is created when radioactive byproducts of a nuclear reaction, either man-made or natural, are dumped in the environment or in the vicinity of human settlements. Nuclear power and research stations are the major contributors to man-made radioactive waste. These facilities bring about a nuclear reaction, usually fission, for the purpose of either production of energy, that is electricity, or research. When a heavy atom of a nuclear fuel, such as uranium, undergoes nuclear fission, it results into two daughter nuclei, both radioactive in their own rights. These byproducts aren't reusable and thus have to be dumped. The introduction of these radioactive byproducts in the ecosphere causes radioactive pollution. Radioactive pollution is fast becoming a major concern due to the increase in the usage of nuclear fuel. The radioactive byproducts of nuclear reactions are often disposed without any precautionary measures to isolate the harmful components, and this contaminates air, soil, and water. A large amount of radioactive waste is generated from nuclear reactors used in nuclear power plants and for many other purposes. It may also occur during extraction and refining of the radioactive material. Radioactive waste generates radioactivity and emits radioactive byproducts. The reason why radiation is considered a threat is that it contains enough energy to ionize a stable atom by separating an electron from it. If ionizing radiation enters the body of an organism, it ionizes the molecules found in the body. This leads to the formation of a large number of free radicals that react with vital bodily components, nullifying their effects by forming new compounds in their place. This can lead to cancer.
Some commonly used radionuclides, naturally occurring radioisotopes. Carbon-14, used to measure the age of water, up to 50,000 years. Chlorine-36, used to measure sources of chloride and the age of water, up to 2 million years. Lead-210, used to date layers of sand and soil up to 80 years. Tritium H3, used to measure young groundwater up to 30 years. Artificially produced radioisotopes. Americium-241, used in backscatter gauges, smoke detectors, fill height detectors, and in measuring ash content of coal. Cesium-137, used for radio tracer technique for identification of sources of soil erosion and deposition in density and fill height level switches, also for low intensity gamma sterilization. Chromium-51 and gold-198, used to label sand to study coastal erosion, also a tracer in study of blood. Cobalt-60, lanthanum-140, scandium-46, silver-110M, gold-198, used together in blast furnaces to determine residence times and to quantify yields to measure the furnace performance. Cobalt-60, widely used for gamma sterilization, industrial radiography, density and fill height switches. Gold-198 and technetium-99m, used to study sewage and liquid waste movements, as well as tracing factory waste causing ocean pollution, and to trace sand movement in riverbeds and ocean floors. Hydrogen-3 tritiated water, used as a tracer to study sewage and liquid wastes. Iridium-192, selenium-75, ytterbium-169, used in gamma radiography and non-destructive testing. Krypton-85, strontium-90, thallium-204, used for industrial gauging. Manganese-54, zinc-65, used to predict the behavior of heavy metal components in effluents from mining wastewater. Nickel-63, used in light sensors in cameras and plasma display, also electronic discharge prevention and in electron capture detectors for thickness gauges. Adverse effects of radioactive waste on the environment. Radioactive wastes contaminate soil by transferring harmful substances into growing plants, resulting genetic mutation and affects the plant's normal functioning. Some plants may die after such exposure, while others may develop weak seeds. Eating any part of the contaminated plant, primarily fruits, poses serious health risks. Since plants are the base of all food chains, their contamination can lead to radioactive deposition all along the food web. Similarly, when radioactive waste is washed up in a water source, it can affect the entire aquatic food web. Both terrestrial and aquatic radioactive contamination can culminate in human consumption. Since humans are apex predators, the accumulation of radioactive materials on the last rung of the food chain would be maximum. Both 106 rubidium and 137 cesium have been found to accumulate in fish muscle and in crab cancer pagaris, hepatopancreas, and muscle tissue. Crabs were found to accumulate 144 Ce and 95 zirconium, 95 nibullium in addition to 106 rubidium and 137 cesium. The most significant uptake route for these species is believed to be via the diet. On human beings. Human beings are affected by radioactive pollution in variable magnitude depending upon the level and duration of exposure to radioactivity. Low level exposure may have a mild skin irritation. On the other hand, long term exposure or exposure to higher amounts of radiation can have far more serious health effects. This can result in irreparable DNA damaging leading to a life-threatening condition. Continuous exposure to radioactive substance lead to ionization of large number of molecules inside the body into free radicals. These free radicals then increase the rate of multiplicity of cancerous cell, that is, tumors in the body. People with heavy radiation exposure are at very high risk for cancers. The cells undergoing rapid cell division are more sensitive to radioactive pollution, such as skin, bone marrow, intestines, and gonads. On the other hand, cells that do not undergo rapid cell division, such as bone cells and nerve cells, are not damaged so easily. Skin cancer, lung cancer, and thyroid cancer are some of the common types of cancers caused by radiation. The small amount of exposure to radioactive substance can be dangerous to human health and environment. Prevention measures can be taken because radioactivity can be detected by various devices. The Geiger counter or scintillation counter is universally used device to detect radioactivity. Classification of waste. Low level waste. They contain negligible amount of long-lived radionuclides. The level of short-lived radionuclides are also generally low. They are produced by peaceful nuclear activities in industry, medicine, research, and by some nuclear power operation. Such waste may include items like gloves, rags, glass, small tools, papers, filters, washing, etc., contaminated by radioactive materials. Intermediate or medium level waste. They contain lower levels of radioactivity and comparatively lower heat content than high level wastes, but require shielding, handling, and transport. They may include resins from reactor operations, solidified chemical sludges arising from treatment of low-level liquid waste, and or pieces of equipment or metal. Radium-226 and americium-241 are used in research under biological and or agricultural sector. These require long-term management and disposal as intermediate level wastes. High level waste. They arise from reprocessing of spent fuel from nuclear reactors. Spent fuel elements stored at reactors Spent fuel elements stored at reactor sites also fall into this category. They contain transuranic elements and fission products with high radioactivity and long lived. Waste management. Objectives of waste management. Radioactive waste management has the safety and environmental objectives. First, to comply with radiological protection principles for the present and future generations. Second, to preserve the quality of the natural environment, that is, to maintain the ecological balance of life forms, including man, to minimize any constraint on future generations as far as practicable. Principles and philosophy of waste management. Three main principles that govern the management of radioactive wastes are: first, dilute and disperse waste to environment through effluents containing radionuclides in amounts far below the authorized radiological protection limits. Second, delay and decay these wastes which contain only short-lived radionuclides. Third, concentrate and confine those wastes which contain significant amounts of long-lived radionuclides. The effects of radioactivity can be nullified by three ways. Time. Get out of the contaminated area as fast as possible. Distance. Get as far as from the contaminated area. Radioactive particles owe their destructive capability to their initial velocity, which enables them to penetrate our skin. The particles lose velocity over long distances and thus can't penetrate the skin. Shielding. Shielding is used in occupations where contact with radioactivity substance cannot be avoided. Lead is majorly used as a radiation shield. Treatment. The radioactive pollution can be minimized by storing radioactive substances for an appropriate time before dumping. Generally, after a period of 7 to 10 half-lives, the radioactivity could decay appropriately so as to allow the contents to be disposed into municipal dump or as normal waste. The radioactive waste can be treated depending upon the state of waste under the three heads: solid, liquid, and gaseous. Solid. Solid waste are generally treated as first for volume reduction by compaction or by incineration. Further treatment of wastes so reduced in volume depends on their level of activity. If such wastes carry low and short-lived activity, they are put directly in shallow earth trenches. If they contain higher radioactivity with longer half-life, they are put in RCC trenches either directly or after mixing it with concrete in drums. If solid wastes are highly radioactive with long-lived nuclides, they are first immobilized in concrete bitumen and further covered by adequate thickness of concrete. Containment of such deep trenches is further improved by steel lining if necessary. The location of storage disposal sites is selected after thorough site investigation in terms of geohydrology, geochemistry, and other soil and subsoil characteristics. Liquid. Liquid wastes, by their very mobile nature, need to be stored carefully and managed efficiently. Their treatment depends on their category. Low level waste. These treatments are specific with respect to sites and the operations and consist mainly of chemical precipitation and ion exchange treatment. The treated effluent is then discharged into water body after ensuring adequate dilution. The sludge, solid, or the resin containing radioactivity is fixed in cement matrix and disposed of as solid waste. Intermediate level waste. The intermediate level waste, mostly from fuel reprocessing plant, are chemically treated in a way similar to low level waste. The sludge, ion exchange resin are conditioned in bitumen matrix and then stored. More recently, polymer matrices have been used for immobilization of spent ion exchange resins and higher active waste concentrates. High level waste. It arises from the processing of spent fuel for the recovery of plutonium. Practically all the radioactivity, 99% or more, is first concentrated and then stored in liquid form in stainless steel tanks surrounded by concrete shield and cooled with water if required. Gases. These wastes are mainly in the form of ventilation, air, and in few cases consist of volatile products generated during certain chemical reactions. Its management is an integral part of general plant ventilation system and takes place at or near the plant sites. The degree of decontamination filtration required for the exhaust air coming either from the vessel, a cell or general ventilation is worked out in advance and scrubbers, charcoal filters, absolute filters, HEPA filters are installed accordingly. It further involves the combination of principles, that is collections and concentration of air through a well-designed stack. The height of stack and efflux velocity through it are so chosen that the ground level concentrations after atmospheric dispersion at the site boundary are within the allowable levels.
The threat of radioactive waste can be minimized to a great degree or even completely negated if it is stored for an appropriate time before being dumped. Normally, after a period of 7 to 10 half-lives, the radioactivity could decay sufficiently so as to permit the contents to be disposed of into the municipal dump as normal waste. Generating electricity or getting other useful products from nuclear reactors is not free from dangers. There have been many accidents in the past. Let us consider some of the case studies. With nuclear technology rapidly taking the spotlight in the last 50 years, radiation accidents seem to be a harsh reality of the modern world. Let us discuss three case studies related to the radioactive pollution. The first case is Chernobyl disaster. It was a catastrophic nuclear accident that occurred on 26 April 1986 at the Chernobyl nuclear power plant in Ukraine under the direct jurisdiction of the central authorities of the Soviet Union. An explosion and fire released large quantities of radioactive particles into the atmosphere, which spread over much of the Western USSR and Europe. The Chernobyl disaster is the worst nuclear power plant accident in history in terms of cost and resulting deaths, and is one of only two classified as a level 7 event is the maximum classification in international nuclear event scale. The battle to contain the contamination and avert a greater catastrophe ultimately involved over 500,000 workers and cost an estimated 18 billion rubles. During the accident itself, 31 people died and long-term effects such as cancers and deformities are still being accounted for. A second accident occurred in 2011 at Fukushima Daiichi nuclear power plant in Japan. The powerful earthquake which hit Japan on 11th March 2011 caused a tsunami which caused the destruction of millions of people's homes and livelihoods. A consequence of this terrible natural disaster was a follow-up man-made disaster, that is, a nuclear power plant which supplied electricity to thousands of homes was also damaged by the tsunami. Not long after the disaster, it was announced that radiation had been found in water in Japan's capital city, Tokyo, and that it was unsafe for babies to drink this water. Tokyo is 220 kilometers away from the radiation leak. In April 2011, it was announced that the level of concern surrounding this nuclear disaster had risen on a scale from level 5 to a maximum of level 7. This sudden jump to a warning of level 7 did not mean that things suddenly became worse at the power plant. In fact, the plant was earlier leaking less radioactive particles. The third incident occurred in Delhi in India. That is referred to as the Mayapuri radiological accident. In April 2010, the locality of Mayapuri in New Delhi, India was affected by a serious radiological accident. An AECL gamma cell 220 research irradiator owned by the University of Delhi since 1968 but unused since 1985 was sold erroneously at an auction to a scrap metal dealer in Mayapuri on February 26, 2010. The orphan source arrived at a scrap yard in Mayapuri during March, where it was dismantled by workers unaware of the hazardous nature of the device. The cobalt 60 source was cut into 11 pieces. Each piece was bright and shining. The owner of the junkyard, Mr. Ajay Jain, was tempted to keep the smallest piece in his wallet. 2 fragments were moved into a nearby shop, while the remaining 8 remained in the scrap yard. All these sources were recovered by mid-April and transported to the Narora Atomic Power Station, where it was claimed that all radioactive material originally contained within the device was accounted for. The material remained in the custody of the Department of Atomic Energy, India. 8 people were hospitalized as a result of radiation exposure, where one of them later on died. With nuclear technology rapidly taking the spotlight in the last 50 years, radiation accidents seem to be a harsh reality of the modern world. 2 years thereafter, a study was designed to assess the awareness and practices regarding radioactive waste among scrap dealers, aiming to assess deficiencies in radiation disaster preparedness. Dear students, let us recapitulate what we have learned in this chapter. Radioactive elements come about naturally in the environment from the weathering of atomic minerals. The 3 main types of emissions from radioactive substances are alpha radiation, beta radiation, and gamma radiation. Radioactivity is the spontaneous loss of energy from an unstable nucleus in the form of various nuclear byproducts and lead to atoms' stable configuration. The radioactivity may contaminate and propagate through air, water, and soil as well. The main issue is the fact that nuclear waste cannot be degraded or treated chemically or biologically. Sealed radioactive sources are used in industrial radiography, gauging applications, and mineral analysis. Short-lived radioactive material is used in flow tracing and mixing measurements. The continuous analysis and rapid response of nuclear techniques, many involving radioisotopes, mean that reliable flow and analytical data can be constantly available. Radioactive waste generates radioactivity and emits radioactive byproducts. The reason why radiation is considered a threat is that it contains enough energy to ionize a stable atom by separating an electron from it. The rapidly growing or dividing cells like those of the skin, bone marrow, intestines, and gonads are more sensitive towards radioactive emissions. On the other hand, cells that do not undergo rapid cell division, such as bone cells and nerve cells, aren't damaged so easily. Skin cancer, lung cancer, and thyroid cancer are some of the common types of cancers caused by radiation. Some countries have well-regulated industries and manage radioactive waste appropriately. In particular, there are regimes in place nationally and internationally for managing high-level radioactive wastes. However, in others, especially the poorer ones, there is little appreciation of the scale of the hazards related to uranium mining and processing wastes, and little or no industry or government effort to deal with the problem.